So now, of course, at one loop you could just do things like this as well. So you use up your loop there or something. I don't care about that. I am trying to only do this. First, I want to show you that an effective vertex can show up in different ways. So I'm just alerting you to that fact that a robot would have a pickup, right? They would go through all the ways that you could take the phi's here and contract them with the phi in your question. But the real reason I'm doing this is to figure out this number. Okay, so, and then there's plus counter terms. So, but of course, you see, the reason I'm trying to calculate this is because the reason I've gone to this thing here is because the Feynman rules in this language for connected diagrams you already know. You already know what the rules of the game are, including all the combinatoric factors. So I'm just going to use that to tell me the answer there. Okay. And so comparing with usual connected diagram combinatoric factors implies that the number is 1 over 8. And we can see that easily by this, that, where does this 8 come from? If I have the 1/8 there, then there are, so again, there are these, this thing has a kind of a phi squared x structure and a phi squared y structure. Two phi's meet at the same space-time point, and the other two phi's meet at the same space-time point. If you think of this as a kind of effective vertex with some coefficient gamma x comma y, right? Integral d for x, d for y. Then when you contract with the phi's in your question, each of if you want phi 1 to contract with this phi of x, it could contract with the first factor of phi of x or the second factor of phi of x, and that's a factor of 2. Then it could contract with, but then on this side, the phi of 3 could contract with the first phi of y or the second phi of y, and that's a factor of 2, so that's a factor of 4 totally. And then this thing is invariant, I mean, this thing is insensitive to whether I switch x and y here, okay? If you think of it as just this effective vertex, this x and y, as you integrate over all x and all y in order to form the real space-time Feynman diagram for gamma, the x and the y could just trade places. So there's an extra factor of 2, even though in this diagram, these two lines want to go to the same point, these two lines want to go to the same point. The diagram would look the same if I said these 2 points go to y and these 2 points go to x. Wouldn't know. So that's an extra factor of 2. So that's 2 times 2 times 2. There's a 2 times 2 times 2 overcount that you're getting when you're hooking up these lines to this effective vertex. Okay? So I've said it, play with it to make it your own. That's where this 1/8 comes from. Okay, corresponds to 2 ways to contract external line with, say, phi squared x times 2 ways for external line contract with phi squared y times 2 ways to label phi squared as phi squared x versus phi squared y. So that's it. That's it. Now I can go back to where I want to go.
So this strange symmetry factor that's sort of different, is that just coming from the fact that we amputated it, or does it also have to do with
it's coming from the fact, as you see, the amputation has lost the identity of this line as going to the source on the moon. This is Moon, Earth, Mars, Pluto. So it doesn't know where it's headed at this level. And that's exactly the amputation. If you want, it's entirely because of the amputation.
Okay.
But it's easy when you just draw some connected diagram that involves this to quickly deduce what this guy had. So, for example, if you read Peskin and Schroeder and you look at the same one-loop renormalization story, it's done at this level. And so you don't go through this little exercise. But the price you then have to pay is that the program of renormalization, which is made to look as straightforward as possible at the level of effective action, because the effective action has got the same argument as the action and as counterterms, and so everything is sort of roughly of the same species. You lose that when you work in terms of these Green's functions. But that's why I've asked you as homework to read that chapter as well, because best case, you know both ways of thinking about these things. But I think conceptually there's no question to me that this effective action way is the right way to think, and we're going to make use of it when we get to QED, and we'll see it even more so. So back to where we were the other day. Which was staring at so for a little while, since I hate factors, for one, I am going to neglect keeping track of all these pure numbers, 1/8 times 1/2. And I'll just put them, but when you see where I put them back at the end, it'll just be reminded that this is where they came from. So now I'm working on the analytic form, which is much more interesting and much more important. These factors do play an important role in the physics, but not yet. Okay, so this thing is at least proportional to where we were the other day, which is something of order lambda squared. I want to at least recognize that it happens in second order. Integral lambda squared, integral dx, Feynman x 0 to 1, integral d4q, and then after, so we have this representation. So the total momentum here is p, if you want p1 plus p2. But in this Feynman diagram, this is all that appears, plus m squared plus p squared x 1 minus x whole squared. Okay, so it looks very similar to the kind of thing you saw in the self-energy calculation, that it can be written using Feynman parameterization as a total square in the denominator, which is technically nice because after I do the shift in the change of variables in momentum, this is equal to lambda squared and then it's just q squared. Oh, and I've quick rotated. So this is all Euclidean momentum except for p. Then looks like okay, so this is where we were as well today, at the end of class, like today. And so that's that. Okay. Now, to dim ray. Okay. So we are about to see that this is a function of m, it's a function of p, but it's also a function of the number of dimensions of space-time, which normally we just set at 4, but we are going to consider, so generalize, we're going to generalize to lambda squared integral dx 0 to 1, integral d4, sorry, dq Euclidean q squared plus m squared plus p squared x 1 minus x. So what we're going to see is that this possibly d is going to be, in fact, not only is it going to be not an integer, not only is it not going to be 4, it's not necessarily, I'm generalizing it not even to be an integer, not even a real at the end of the day. But the main thing that you need to know first up is in what sense is this going to be a regulator? Okay. Well, we're going to find a way of generalizing this so that it is seemingly a nice analytic function of d. Think smooth function of d. So if d is very close to 4, who cares? It's so close that the function evaluated for d equals 4 minus 0.00001. Who cares whether I stuff in that or I stuff in 4 itself? Now, that'll turn out to be true, that this and this are close approximations, because I'm not going to move very far away from 4. This and this are going to be close approximations. And if this integral converged, then indeed it is really doing almost nothing. The difference between this for d very close to 4 and d equals 4, the two things would actually be essentially, would be so close to each other as to make no difference. But this integral is divergent. And we are going to try and make sense of this for complex d. And the only place it makes a difference is for the divergent part. Okay? So the infrared part of this and this, I'm going to try and show you in midstream. You're not really changing anything very much as long as this d is not very different from this 4. But for the divergent parts, you're completely changing everything, which is good, because a regulator is something that tremendously changes the far ultraviolet of these loop integrals so as to actually render them finite and at least mathematically sensible. not changing, not modifying the infrared part, the low Q part of the integral. That's what we mean by a regulator. Of course, the price that you're paying a regulator is that whatever is doing the modifying in the far UV to make it finite doesn't make physical sense. No more is that true than in the case of dimensional regularization, where the thing that's making it finite is by changing the number of dimensions to a complex number. Okay? But that's just like breaking spin statistics or thinking you live on a space-time lattice. You don't really believe any of those things, and you don't really believe the number of dimensions is complex. Okay, that's the viewpoint you should have, but the main thing is that we're not modifying the behavior of the low Q part of this integral. Okay, so let's see how that's true. Now, first, what am I supposed to even do with this? And the idea is, let's keep processing this. It's like you're trying to invent the gamma function or something, but all you know is n factorial. Well, let's keep processing this as if d was a general integer. At least then we know what we're talking about, right? It's an integral. You work in Euclidean d-dimensional space, and at least we know what this integral means. Well, what we would do is just, since this is q squared, we would just work out this in polar coordinates. So let's just do that. In fact, we did do it earlier. Let me just count what happened. So what do I call it? This thing is not worth writing again and again for a while, for a little while at least. So the Peskin and Schroeder called it delta, and nothing wrong with that. So let's call it delta. By which I mean just something independent of, it's a complex number independent of q squared. Of course, there's a plus I epsilon there. It's a complex number independent. No, there isn't. Sorry, there is. The I epsilon is telling you. So that's minus. The I epsilon is telling you if once you get the function of delta, and if the function of delta has some branch cuts or something like we saw in the self-energy, the I epsilon tells you how to whether to go above the branch cut or below the branch cut. So I've forgotten that. Look at the self-energy. Okay, so there to. So we clearly are interested in an integral that has the following form. Euclidean integral, and it looks like this. Delta squared, where delta is some complex number. Okay? This is easy. It's just the integral. This is the what's it called? Angular integral in d dimensions. And here is the 2 pi to the d, because I would put 2 pi to whatever space-time dimensions I am in, and not 2 pi to the 4th, 2 pi to the d. That's what the slash means in the slash notation there. And times the radial integral, which is integral dq from 0 to infinity, q to the d minus 1 over q squared plus delta squared plus delta squared.
So this spherical,
Spherical, yeah.
Is that one d
This
minus
is
1?
so. This is just the area or volume.
I know, but is it d minus 1 sphere or d?
Yeah. I don't know what Peskin's notation is. He might actually call it omega d. So beware, because it's either the sphere in d dimensions or it is the d minus 1 dimensional sphere. So, but you understand the logic. So recall, we once had to do four-dimensional angular integral in the self-energy case. And while I was at it, I just did the n-dimensional angular integral. So I already gave a formula. So recall that integral d omega d, again, just thinking of it as an integer, is equal to 2 pi to the d over 2 over gamma d over 2. Okay. Then this thing here, this integral, is some function of delta, but it is equal to a half, so we just prefer to use the dq squared variable, so that's easy, it's q squared to the d over 2 minus 1 divided by q squared plus delta. And this is equal to, so I'll let you check, it's a very simple check, but it's not, I at least couldn't see it right off the top of my head, but it's a very simple change of variables. You're changing to x. C. Okay? And then this thing becomes 1 over 2 delta to the 2 minus d over 2. And this integral, which is better known, dc from 0 to 1. C to the 1 minus d over 2. And 1 minus c to the d over 2 minus 1. So, our I is this integral times this integral. Now you will notice that at the level of just looking at these functions of d, there's nothing here that doesn't make sense for d in the complex plane. Because we massaged it far away from doing a multiple integral, d times. This doesn't know that it came from a d-dimensional multiple integral. And similarly this, even if this d over 2 is complex, is a reasonable function of d. We'll study where it blows up, but for general d, it makes sense. And even here, the function of d makes sense. So in that sense, you'd say, well, if this is operationally for integer d, like the one that we really care about, this is, I haven't changed anything, but it seems like I can make sense of Feynman diagrams in this sense as functions of some sort of non-integer d. Okay. We don't know what possible sense to assign to it, but if it helps us to regulate the ultraviolet in a simple way, then we're willing to pay the price. Okay? Without asking questions. So this form of the integral is useful because there is a standard identity or standard result of doing this integral. That is, there's something called the beta function in mathematics as opposed to physics, which is called b of alpha and beta, function of two variables, and it is got an integral representation, which is integral dc from 0 to 1, and c to the alpha minus 1, and 1 minus c to the beta minus 1. And what is this integral? Well, the answer is simply the gamma function of alpha, gamma function of beta, over the gamma function of alpha plus beta. Okay, so all we have to do is stuff in our particular values of alpha and beta. And we have now, at least in terms of gamma functions, we've written everything. And so therefore, I is equal to 1 over 4 pi to the d over 2, check, and then gamma of 2 minus, so some of these gamma functions cancel between the angular integral and the radial integral, but we get left with this, 1 over delta, the 2 minus d over 2. Okay,
Is that a gamma of 2?
say again?
In the denominator, is it just a gamma of 2?
Gamma of 2, so I've written it as gamma of 2 only as sort of the literal robotic writing out of these formulas, but of course you can drop gamma of 2 as well. Okay? So the integral has lost all, we've massaged it to the